Well, next we look at what happens if your applied force is in some direction other than horizontal. Okay, what does that do to the analysis of this situation? Well, the applied force is, in every sense, equivalent to the sum of its projection on the horizontal direction, which I'll call F applied horizontal, and its projection on the vertical direction, which I'll call F applied vertical. Okay, so that this vector is the vector sum of this vector and this vector, and so it's completely equivalent, so we can cross this vector out and just replace it with these two vectors. Now, I do a diagram down here where I kind of do that. I don't really cross out this vector, but down here I write it very lightly, and then I write its components, its projections on these two directions in dark purple, okay? And then we do a little bit with this. But the idea that we have to have then is that this is equivalent to a horizontal force and to a force exerted straight down on this block, okay? Now, the force exerted straight down on this block means that the tabletop has to exert more upward force, and that increases your normal force. Now, if I were doing this following the equations and so forth and not really thinking about what's going on, you might miss that. And people do tend to miss that. They think, okay, normal force, you got gravity down, normal force is equal and opposite. Well, yeah, if there are no other forces in the vertical direction, that's going to be the case. If there are any other forces in the vertical direction, whether downward or upward, that changes your normal force, because the tabletop either has to exert more or less force than if it was just supporting the block. Okay, so here's our picture. Actually I did go ahead and do the calculation of these forces, which is very straightforward. We'll come back to that in a minute. Here's our frictional force, here's our 50 Newton force of gravity, here's our normal force. Okay, now, I assumed something that wasn't on the worksheet. I assumed that the applied force had a magnitude of 50 newtons. Okay? Now, I think on the worksheet the stated or implicit assumption is that you're exerting the same amount of applied force but exerting it 30 degrees below horizontal. And I'm not sure I stated that with complete clarity. Okay, I haven't looked back, but I suspect maybe I was a little careless with that. In any case, if this is the magnitude of the applied force, then what is this projection and what is this projection? Well, from what we did with projections, we know we have a right triangle here, and we have a 30-degree angle here, so that this side of the right triangle, which is going to correspond with the projection in the horizontal direction, is going to be what? It's going to be the adjacent side of a triangle where the applied force is the hypotenuse and the angle is 30 degrees, so it's going to be F applied cosine 30 degrees. Okay, whatever F applied is. This component, well, we can actually get it from the same triangle and find that it's going to be, its magnitude is going to be that of the applied force times the sine of 30 degrees. However, this applied horizontal force is in the positive direction. This appears to be in the negative direction, so we put a negative sign in front of it. Okay? And then we calculate it based on the 50 newtons. We get negative 25 newtons for this force. And what does that do? Well, that means we got an extra 25 newtons pushing down. It means we've got to have an extra 25 newtons of normal force to push back up. Now we want to be able to organize that information in a very systematic way so we don't get messed up by whatever assumption might cross our brain and mess everything up, because these problems can get rather complicated. But that's the idea here, and this is a relatively simple situation. Now I'll say one other thing, and in this course we will generally measure our angles counterclockwise from some chosen direction. in that direction will usually be our x direction. And as we'll see next time, our x direction is not always horizontal. There are reasons we would want an x direction to be other than horizontal. So our coordinate system would rotate from the horizontal, but we'll get to that. So assuming our coordinate system has an x direction here and a y direction here, the angle of this applied force would be 330 degrees, the circular angle that we get when we go counterclockwise from the positive x direction around to the vector. Okay, and it's very clear that that will be 330 degrees. You got a 30-degree angle here. If we went all the way around to here, we would have gone 360 degrees. We go 30 degrees less, so it's 330 degrees. The advantage to using this angle is that we never have to ask ourselves, well, is this positive or negative? That's obvious in this case that it's negative, but it's real easy to overlook that sort of thing if we're always thinking about is it positive or negative. Intuitively, it's important that we think about that, but we don't want to let our mathematics rely on our intuition. So if we want to do this mathematically and correctly and precisely, we use the circular angle, which takes care of whether this component is positive or negative. So we just multiply the applied force by the cosine of the angle, and we get this. Now the cosine of 330 degrees is the same as the cosine of 30 degrees, as you should know if you know your trigonometry. If not, ponder that. If you can't get it, email me or ask me. The sine of 30 degrees, on the other hand, is not the same as the sine of 330 degrees. Okay? If we use this angle, the circular angle, we'll automatically get the negative sign when we do the 330 degrees. So we don't have to write a negative here. We just say it's F applied times the sine of 330 degrees, and that is negative 25 newtons. Never having to think about whether that's positive or negative, it comes out of our calculation. And then, of course, we do want to think, well, okay, why is that negative? So we go back, okay, yeah, that's below the axis. We've got a downward component, and that will be in the negative y direction. Okay. Now, how do we use this information? Well, here's our picture. Now, we've got our normal force here. We've got our gravitational force here. We've got our vertical component of our applied force. We've got the horizontal component of our applied force, and we've got a frictional force indicated here. We don't know how big to make that because we don't know how big our normal force is going to turn out to be, although it's going to be bigger than what I've actually drawn, and this will actually be quite a bit bigger than what we've drawn. Still, we have a picture that we can use to set up these equations. Okay, now, in the vertical direction, we have our normal force, our gravitational force, and the vertical component of our applied force. That all has to add up to 0. From this, we determine that the normal force is the negative of the gravitational force minus the applied vertical force. Now we've got to think carefully about what that means. The gravitational force is downward. So on a coordinate system where x is here and y is here, that would be negative 50 newtons, wouldn't it? But we have negative the gravitational force. Negative of negative 50 newtons is positive 50 newtons. Now if we didn't have the applied vertical force, our normal force would be just the negative of the negative 50 newtons. As before, it would be 50 newtons upward. But we have this applied vertical force, which is a negative 25 newton force in the vertical direction. And we do minus that because, you know, when we move these things over to this side, they become negative, don't they? Or we get the negative of whatever they are. We have a minus of the negative 25 newtons. That's plus 25 newtons. We have 50 newtons here, 25 here, adds up to 75 newtons. That's our normal force. And this is in the vertical direction. In the vertical direction. Okay, well then we conclude that our frictional force being 60% of, being equal in magnitude to 60% of the magnitude of our normal force is 45 newtons, and that's going to be to the left. If to the right is positive, then we conclude that our net force is our applied horizontal force plus our frictional force. Now that is our total net force. and I didn't use vectors here because I'm being a little careless. We've already established that we have zero net force in the vertical direction. That's how we got all this, and that's because we have a strong enough tabletop here, okay? In the horizontal direction, we have then 43 newtons from our applied horizontal force, and that's what we get if we multiply 50 newtons by the cosine of 30 degrees. But we have a negative 45 newtons in our frictional force. Well, that would give us a net force of negative 2 newtons, meaning that the thing would be accelerating in this direction due to the fact that the frictional force is bigger than our applied horizontal force. But our frictional force can't make something move in its direction. The frictional force always opposes motion. So this calculation can't be right. And this is simply because the frictional force is limited by the fact that the frictional force combined with another force can't give us anything in the direction of the frictional force, okay? So the frictional force can't be bigger than our applied horizontal force. So the frictional force actually would turn out to be 43 newtons in this case. So that's something you have to think through. I'll just say it can't be because friction can't result in motion in the direction of the friction. Friction is a force that acts in the direction opposed to motion. If there's going to be any motion in this situation, it's going to be in this direction, because there are no forces other than the frictional forces in this direction. So that's an idea that you simply want to sort out.